Hello and welcome to Bay College's Intermediate Algebra Online Lectures. My name is Jim Helmer, and in this video we're going to discuss section 6.1, Roots and Radicals. And essentially what a radical is asking is, in one example, is what numbers squared will give us 49. Now, in mathematical symbolic terms, we have the square root of 49. That's what it asks. What number times itself will give us this 49? And we're going to discuss a little bit about indexes and the radicand. We'll get a little bit more into that. When we have a square root as an example, there are two possibilities. The first one being positive. Well, what number, positive number, times itself would give us 49? Well, the positive result would be 7. That's a positive number. 7 times 7 is in fact 49. So what number is squared? Well, 7 is one of those possibilities. The other possibility might be negative 7, because negative 7 times negative 7 is also 49. Because a negative times a negative is positive, and 7 times 7 still results in 49. But what if it asks us, what is the square root of negative 49? What two numbers multiplied together, or what number multiplied by itself, would give me negative 49? Well, in the real number system, our solution to this is no solution, because there is no real number when multiplied by itself that will give us a negative number, because a positive times a positive is a positive, and a negative times a negative is a positive. So there is no number times itself that'll give us negative 49, at least no real number. So when we see the square root, or maybe a fourth power root, we'll talk about those indexes shortly. If it's an even root, negative value under the radical, it's no solution, or no real number. We might want to write out no real number. All right, let's look at some examples here. We have the square root of 16/25. Now, we'll talk about perfect powers in a minute, but since this is a square root, our index is 2. We assume 2 because that is the first value that we can start having indexes. 1 wouldn't make sense. What's something to the first power? Well, it's itself, right? So we have the square root of 16/25. Well, we can take this a little piece at a time. The square root of 16 is 4. The square root of 25 is 5. So what number times itself would give me 16/25? Well, we could have positive 4/5 times positive 4/5 is 16/25. So we could have 4/5. We could also have negative 4/5 times negative 4/5 to give us that same result. But we're going to look at what we just look at the positives for now, right? Because in this example, we have the square root of a negative. Well, what value times itself will give us a negative? Well, there isn't a real value. So we say no solution. So hopefully we recognize that. Sometimes we got to be very careful about where that sign is. We don't want to make a sign error. Here, that negative's on the outside. And if we think of our order of operations, you work within the innermost grouping symbols and follow our order of operations and work out. So we can think of this radical as a grouping symbol. Let's work within the inside. Well, 16/25, it is what it is. We're going to move out a little bit. What is the square root of 16/25? Well, that would be 4/5. And then we apply this negative. We think of this as maybe a negative 1 times this quantity. Well, negative 1 times anything just changes its sign. So this answer would be negative 4/5. All right, we're going to look at cubed roots as well, and higher powered roots. But what do we know about odd numbers? Well, if I have a negative times a negative times a negative, 3 negatives multiplied together will still result in a negative, or 3 positives will still result in a positive. So if we look at this, we say, well, what is the cubed root of 8/27? Well, hopefully we recognize 8 as being 2 times 2 times 2, a perfect cube number. So the result here would be 2 over 3 times 3 times 3 gives us 27. So what number to the third power would result in 27? Well, that would be 3. So this is 2/3. Now, the interesting thing about odd roots is an odd number of negatives results in a negative number. An odd number of positives multiplied together results in a positive number. So the sign doesn't change when this index is an odd number. So the result here would be negative 2/3. Now, I just want to point out the difference between this one, an even root, a square root, our index is 2, and this one, odd root, our index is 3. We can have negative values if this index is an odd number. All right, well now let's assess this one. It's a little bit different. We have a variable in here, and what we're going to look at is the square root. Since there is no index indicated, we have to assume it's 2. What number, and we can break this apart. So let's deal with the number first. What number times itself will give me 36? Well, 6 times 6, because 36 is a perfect power of 6 squared. And then we can move to the variable. Well, x to what power would give me x to the 8th if I multiplied it by itself? Well, x to the 4th times x to the 4th, if we recall our rules of exponents, we would add them. So x to the 4th times itself, x to the 4th, would give me x to the 8th. Now, one thing about this, and some textbooks and some instructors are a little bit more persnickety, so to say, but we're looking for the positive or the primary resultant here. So we throw in these absolute values because this is going to give us a positive value, because what's under this radical cannot be negative, okay? But in this case, we're raising it to the 4th power, an even value. So even if x was a negative value, it's still in the domain in this case. So the absolute value we just put there, kind of like a catch-all. All right, let's kind of review some of our perfect powers. Perfect power numbers, if we have these memorized at least up to a certain amount, it's going to make our lives a little easier when it comes to our intermediate algebra math class. One, if you'll notice, is a perfect square, cube, 4th power, 5th power. It's a perfect any power number, because 1 times anything is still that number. Well, 1 times itself, no matter how many times, it's still going to be 1. All right, 2 squared, so if we're looking at our squares, is 4, 3 squared is 9, 4 squared is 16, 5 squared, 6 squared, 7 squared, 8 squared, all the way up to 13 squared, which is 169. If we can recognize these numbers, if I see 49 under a radical, I say, hey, you know, I recognize that as 7 squared. We also have cubes, you know, recognize 1, always a perfect any power. 2 cubed is 8, 3 cubed is 27, 4 cubed is 64, 5 cubed is 125, and 6 cubed is 216. So if we can recognize these are going to make our lives a little easier. These are perfect power numbers, perfect squares, perfect cubes, perfect 4th power, and perfect 5th power numbers. As an example, 1 to the 5th power is still 1, 2 to the 5th power is 32, 3 to the 5th power is 243. What if we have non-perfect powers? What if we're taking the square root or cubed root of non-perfect powers? Well, these result in irrational numbers, okay? These would result in rational numbers, whole numbers, even if they were fractions like this. We see 16 and 25 being perfect powered numbers. But if we, as an example, if we take the square root of 2, well, what number times itself is 2? Well, we end up estimating these. If we put it into a calculator, we don't get a rational number. We get an irrational number. In this case, 1.414 something, something, something. That number would continue on indefinitely with those decimals. So at some point, we'd have to round it. Same thing with the cubed root of 7 as an example. We get 1.912 something, something, something. We end up rounding it. And here in this example, we get 1.913 if we round it to that decimal place. So if we recognize perfect power numbers, take the time to memorize these, or find some way to recognize these perfect powers. And one way to do that is just factor numbers down, so you can see what their factors are and their multiplicity, how many of them are being multiplied together. All right, so let's define a little bit more what it means to be a radical or a root. This is our generic radical where n is the index. It's saying this is how many times I'm looking for this number to be multiplied together to give me this value here, the radicand. And we call that the radicand, or radicand. I think it's radicand, sorry about that. And that gives us our result. And some real number in this section, we're just looking at real numbers. As we move in the course, we'll actually move into imaginary numbers, but for now, we're just looking for real numbers. So when we have even indexes, this is one thing to recognize. Look at that n. Is it an even number? Is it 2, 4, 6, 8, 10, what have you? If it's even, we're looking for a positive real number as our radicand. If it's a negative number, we have no real solution. So A, our radicand, must be positive. And when we have odd indexes, well, it really doesn't matter. It could be positive or negative, because if we have an odd number of negatives being multiplied together, we can get a negative. If we have an even number, an odd number of positives, of course, that's still going to be positive. So let's look at some examples and some properties. One property of radicals is, what if we have powers within the radicand? Well, sometimes we have to assess those, and we could go into great detail when it comes to order of operations and things like that and our rules of exponents, but at this point in algebra, we're hoping that you've covered your rules of exponents at some other point in another math class. But if we look at this generic example, the nth root of a to the n, okay, we can think of this as a fractional exponent. We have a to the n raised to 1 over n. We're saying what number times itself, or times itself n times, would result in a to the n. Well, we think of this as n over n, which is just 1. What's any number to the first power? That would result in a. And if I break this down a little bit more, essentially what I'm saying is we have a to the n raised to the 1 over n. This is essentially what a radical is. It's just a fractional exponent. And if it's a fractional exponent, we can treat it using the rules of exponents. And hopefully those we remember, a to the n over n, which is essentially a to the 1, which is just a. All right, so let's look at this example. We have a square root. We have no index, so we assume 2. So we have the square root of 4 squared. Well, what is the square root of 4 squared? Well, the square root of something squared is that value, so we get 4. Here we have the square root of the quantity negative 4 squared, and we can think of this in different ways. We could think of this as order of operations where we're going to work on the innermost part. Negative 4 squared would be a positive 16. Negative 4 times negative 4. And the square root of 16 is 4. But we're actually going to think about it this way. Okay? If you square root something squared, you get that value. So we're going to leave it as negative 4 because it's being negative 4 is being squared. We're taking the square root of something squared. What's being squared in this example here? Well, negative 4 is what's being squared. What about cubed roots? Well, that property can stay the same here because 2 is a real number and I'm cubing it, which would be 8. The cubed root of 8 is 2. So we can think of it as 3 over 3, which is the first power. So we get 2. So the easiest way, or the simplest way to think about it when we have this is, if these are the same, you get that result. Same thing here. Cubed root of negative 2 being cubed. Well, we get negative 2. That's what's being cubed. All right, let's look at some examples here. If we look at this example, I have the square root of a squared. Well, if I take the square root of something squared, I get that result, a. Here, if I take the cubed root of a cubed, I get that result, a, because I'm saying what number is being cubed root. Well, a is being cubed, so the result is a. Now, if we look at this, we have the fifth root, an odd number, so it doesn't matter if this is positive or negative. The fifth root of the quantity a plus 3 to the fifth power gives me x plus 3. I think I may have said a, but I meant x plus 3. So we get that result. let's look here. We have the fourth root, an even index, the square root of 5, or excuse me, the fourth root of the quantity, negative 5 to the fourth power. We're going to get negative 5. Now, sometimes when you're looking in the back of the book, it gives you a positive 5 because it's saying the absolute value. Either one is correct. Are we looking at negative 5, or are we assessing it differently? Are we going to say, well, negative 5 to the fourth power, even number of negatives, is going to result in a positive value, and then we take the fourth root, we could get 5. But at this level of algebra, we're just going to say the fourth root of something to the fourth power is that value, what's in these parentheses. Same thing here, the seventh root of the quantity negative 3 to the seventh power is negative 3. Here we don't even think about it because odd can be positive or negative in its result. Now lastly, we have the sixth root of the quantity x plus 3 to the sixth power. Now if you recall the last example that we did at the beginning here, the sixth root of this value, we can just say, okay, well, it is this value. But because we have a variable in here, x, we're not just some number, it's good to put in the absolute values because we want positive values in here. We want to make sure we don't do any domain violations or anything like that. So this value, we want it to be positive. And I know this can be a little bit confusing. And when do I put this in? From this point on, we're going to look at these values and just assume all variables are positive. That way, we really don't need those absolute values. So this is just an introduction to 6.1 and the concepts that we're going to be applying. In the next video that deals with 6.1, we're actually going to look at some of the properties of radicals and how we can use them to simplify some of these examples. But as I'll say many, many times to all my students, practice. You got to practice, know your rules of exponents because that's essentially what radicals are. They're just fractional exponents as we see right here. Okay? So take your time, work on some of these, and keep watching the videos. Thank you.